Today, stereo is taken for granted, but as strange as it may seem, listening in mono is still very common and actually more widespread than you might think. In this video, we're going to talk about mono compatibility and how to make sure your music sounds good everywhere. Portable devices like phones and tablets, or some Bluetooth speakers, are mono, as well as sound systems in places like supermarkets, shopping malls, or very large venues like nightclubs. Moreover, on some devices that offer stereo listening, such as laptops or televisions, the distance between the speakers is very small compared to the listener's position, making the listening experience barely stereo and almost mono. Listening in mono therefore remains a fundamental aspect of any music production, and it's important to know how to properly manage what is called mono compatibility. Mono compatibility is the ability of an audio mix to maintain good sound quality even when played back in mono. Specifically, a mix is considered mono-compatible when, in mono, it doesn't lose important elements, doesn't show significant imbalances, and retains its original impact and clarity. A wide stereo image is more satisfying and pleasant, but it always comes at the cost of poor mono compatibility. And if the mix doesn't work anymore when switched to mono, then that's not good. So, it's necessary to find a compromise between width and mono compatibility, and try to make a mix sound good both in stereo and in mono. Among the tools available to the sound engineer, there are some that can help us assess the mono compatibility of a project. However, to interpret them correctly, it's important to understand what factors make a product stereo and what problems might arise when switching to mono. There are several ways to increase the width in a mix, but in short, they all lead to the same results, introducing differences in intensity, phase, and timing between the two channels. Let's see how these differences work. What problems can arise once the mix is summed to mono, and what to pay attention to when evaluating mono compatibility. By working with panning during the mixing stage, you can create intensity differences of a signal between the two channels. Even though this operation might seem simple, it can actually cause problems when switching to mono. As many people know, mono is created by summing the left and right channels. However, to avoid creating a volume difference between stereo and mono, when switching to mono the volume is also halved, resulting in a 6 dB reduction. We notice this behavior by placing a sine wave in the center and switching to mono. Nothing changes. If there weren't a 6 dB reduction, by summing the left and right channels we would have heard an increase in volume, which didn't happen. So, switching to mono isn't just L plus R, but rather L plus R divided by 2. With this in mind, let's do a test. We'll put a sine wave for a few seconds only on the left, then in the center, and then on the right. Let's render the master. Even though the original sine wave's volume doesn't change, we can now see that there is a difference. When the pan is centered, the signal is 3 dB lower. This is due to the pan depth, which is set by default to -3 dB on practically all DAWs. If we now convert the stereo signal to mono, we see that what was on the left and right is now lower, while what was in the center has stayed exactly the same as before. If we look more closely, we see that the difference in intensity between what's in the center and what's on the sides is 3 dB. So what was on the sides is now 6 dB lower than it was at the start. This is precisely due to the conversion to mono. When the signal is only on the left, for example, R is 0, so L plus R divided by 2 becomes L over 2, which means a drop of 6 dB. The same goes for the right channel. Every time we switch to mono, what's in the center stays the same, while what's positioned on the sides gradually decreases until it loses 6 dB when it's 100% at one extreme. This helps us understand one of the problems we can encounter when switching to mono. If many elements are placed at the edges of the stereo panorama, once we switch to mono, all of these drop by 6 dB, changing the volume balance between the elements of a mix. What seemed like a well-balanced mix in stereo risks becoming unbalanced in mono, losing body or punch. Phase differences between the left and right channels lead to the introduction of what is called acoustic phase cancellation. Acoustic phase cancellation is fundamental in creating a convincing and pleasant stereo panorama, so much so that having stereo width always means having a certain amount of acoustic phase cancellation. And this is exactly the problem, because when you switch to mono, this becomes electrical phase cancellation and the signals cancel each other out. For this reason, if the phase differences are too great, you risk completely losing some elements of a mix when switching to mono. Unfortunately, it's not possible to eliminate acoustic phase cancellation in a stereo product, it would become mono. As a result, it's normal for something to be lost when converting to mono. However, it's necessary to make sure that the acoustic phase cancellation and therefore the stereo width aren't excessive in order to limit degradation when switching to mono. Introducing time differences between when the same sound reaches the two channels simulates a parameter known in psychoacoustics as interaural time difference, or ITD, which is one of the cues our brain uses to determine the position of a sound source. A classic example is the Haas effect. ITD is very pleasing because it's a parameter that recreates a stereo image in a very realistic way. However, it has the drawback of being very poorly mono-compatible, because when summed to mono it always introduces phase issues that together create an effect known as a comb filter. Comb filters introduce peaks and notches into the spectrum of the signal, which can significantly alter its timbre. What you're hearing now is the comb filter caused by summing my voice with a copy of itself delayed by 2 milliseconds. It closely resembles the sound of effects like flanger or phaser, because in fact, the comb filter is at the core of how they work. Another issue not to underestimate when converting from stereo to mono is masking. Spreading signals to the edges of the stereo field can help reduce masking, making a mix clearer and more defined even without relying too much on the equalizer. The problem is that if this isn't managed properly, when you switch to mono, the masking becomes more noticeable, risking a mix that sounds muddy and lacks definition. Once we understand the problems that can arise with stereo, we can better appreciate the tools that help us assess mono compatibility. A very useful tool for evaluating mono compatibility is the Vectorscope, also known as the Lysages figure. It is used to visualize the amplitude, frequency, and phase relationships between two signals. It appears as a Cartesian plane where the left channel signal is shown on the y-axis, while the right channel signal is shown on the x-axis. The values of the two signals determine the position of a point that moves continuously, creating shapes known as Lysages figures. The distance from the origin of the axis indicates the intensity of the signals. To make it easier to read, it is commonly rotated by 45 degrees and displayed inside a circle or semicircle. If there is a signal only on the left, the graph looks like this, while it looks like this if there is only a signal on the right. If, on the other hand, the two signals are identical, the figure looks like this. This, on the other hand, represents two identical signals but with opposite polarity, which therefore completely cancel each other out when switched to mono. A stereo signal that moves within this space has some phase cancellation, but not too much, so it is fairly mono-compatible. Whereas a signal that moves in this space has a large amount of phase cancellation between the two channels, and when switched to mono, the mix degrades significantly. The response time of the Vectorscope is quite fast, so it's normal to see peaks moving horizontally. This isn't a problem because the ear isn't quick enough to perceive them. The important thing is that the signal doesn't stay in this area for too long. In addition to any possible phase issues, a Lysages figure can also show us whether the stereo image is overall centered or shifted toward one of the two sides. If it's centered, the resulting figure is symmetrical with respect to the vertical axis. Otherwise, it's shifted toward the channel with greater amplitude. Furthermore, a graph that shows a lot of activity in these areas indicates that there are many signals with high intensity at the edges of the stereo field. Even if they are generally in phase, when summed to mono, as we've seen, their level is halved, heavily altering the balance of the mix. Some free plugins are Stereo Tool by Flux, Goniometer by Tone Boosters, or M_Stereoscope by Melda Production. Let's see how the Lysages figure appears in some finished commercial products with different characteristics. Another useful tool that simplifies measuring mono compatibility is the phase correlation meter. As the name suggests, it mainly measures acoustic phase inversion, but you can also gather other information from it. It appears as a meter that ranges from -1 to +1, passing through 0. You read it like this: a value close to +1 indicates that the two channels are generally in phase. A value of +1 means that the two channels are identical and therefore the signal is completely mono. A value close to -1, on the other hand, indicates that the two channels are mostly out of phase. A value of -1 means that the two channels are identical but with inverted polarity. This results in the maximum acoustic out-of-phase condition. Finally, a value of 0 indicates that there is no correlation between the channels, meaning the signals are completely independent. So the signals are neither in phase nor out of phase, but rather present a combination that favors neither condition. The correlation meter is intentionally slow in measuring the signal, and this is to avoid taking into account those very brief moments of phase or out of phase that would not be perceived by the ear. This way, we have a visual indication that matches our perception. Considering the slower response times, a finished mix that is mono-compatible should have the correlation meter between 0 and +1, and never between 0 and -1. A signal between 0 and +1, but too close to 0, could still be not very mono-compatible because it indicates that there are many different signals with high intensity at the edges of the image. This doesn't necessarily cause phase problems, but as we saw earlier, when switching to mono, everything on the sides drops by 6 dB, heavily altering the balance of the mix. Obviously, the closer you get to +1, the less stereo width you have. Stereo Tool, Goniometer, and M_Stereoscope also offer a phase correlation meter. Let's analyze the same tracks as before. A more advanced version of the phase correlation meter is the multi-band correlation meter. Essentially, it does the same thing, but instead of working on the entire signal, it splits it into bands and analyzes each one individually. The result is therefore a graph that shows us the phase correlation for the different bands. On the y-axis, we have +1 at the top and -1 at the bottom, while on the x-axis, we see the various frequencies. This approach allows us to see phase issues in more detail, so we can fix them by intervening only in the bands where it's necessary. There's also a free plugin for this, the Correlometer by Vectorscope. Let's see once again how the usual tracks behave. Mid and side is often used to widen the stereo image by raising the side channel. However, if you've seen our video on mid and side, you should already know that this method introduces a constant acoustic phase inversion. Among the techniques for widening the stereo field, this is therefore the least mono-compatible. One thing not everyone knows is that mid and side can also be a useful tool for controlling mono-compatibility. In fact, we can analyze the mid and side channels of our stereo work to check their relationship across different frequencies. If you don't have a spectrum analyzer capable of displaying the mid and side channels, you can download Vectorscope's Span, which is also free. Once we've opened the analyzer, we set it to work in mid and side mode, and this way we can compare the width of the side signal to the mid. Even though there's no strict rule for the ratio between mid and side, to achieve good mono compatibility, the mid should be at least 6 dB higher than the side across all frequencies. Let's analyze the tracks again. In all control room sections and in every monitor controller, there's a button for listening in mono. In fact, with the tools we've seen so far, all we can do is estimate mono compatibility, while the best way to check that a product works well in mono is actually to listen to it in mono. It's not uncommon to find a dedicated mono speaker in studios, usually with a reduced frequency response to also simulate low-quality listening, like that of a portable device. If you don't have a control room section or a monitor controller, you can insert a plugin on the Sessions Master, such as Isolate by TB Pro Audio or Manipulator by Bose Digital Lab, and switch to mono using the dedicated button. Both are free, but require you to create an account. Listening in mono allows you to directly highlight all the mono compatibility issues that may be present in a mix. When switching, it's inevitable that you'll notice a change in the sound. As we've seen, this is due to different causes, and for a proper evaluation, it's important that a trained ear can distinguish between them in order to take appropriate action. A great exercise we recommend is to use all the tools we've talked about to analyze your favorite tracks. Take some time to understand how the problem was addressed and try to find a connection between what you hear and what you see on the tools.